We've seen a lot of resistive-based sensors in this course already, and a typical configuration we've used for these is a basic voltage divider, where we have a voltage source up top. We'll call that V in. One of these is the sensor. We'll call this one the sensor. Let's call it R1. The other one is a static resistor, R2, and we get an output voltage based on this resistor divider. Now the output voltage we can compute as R2, right, the bottom resistor in the voltage divider here, divided by R1 plus R2, and that whole thing times Vn. If I'm assuming that this resistance here is changing, I'm going to substitute this by an R1 plus delta R, where delta R is changing that resistance based on whatever the sensor value is. So in this case, I'd get R2 over R1 plus delta R plus R2 times Vn. Right? And you can already see that this is starting to be a little bit hairy. This is a little ugly in terms of trying to back out, for example, what that change in resistance might be in that sensor. And we can simplify it a little bit further. Let's say in this case that R1 and R2 are both equal, their nominal resistance, right, before anything is changed on the sensor, are both equal to R. And our V out in that case is going to be R over 2R plus delta R. Right? So it's still a little ugly, and that whole thing times my V in here. So it's still a little tough to actually pick out what delta R is. Right? And this key bits here, this is nonlinear. Right? My output voltage is not changing linearly with that change in resistance, which I might want it to do, right? It's easier to read out a linear sensor and get a sensitivity for a linear sensor than hooking up your sensor in this very non-linear sensor interface. It's also not terribly sensitive. Right? If delta R is not very big, this is not going to give me a great readout, but on the plus side, it is very simple. Right? I just need an additional resistor and I'm good to go. Right, and let's look instead at another very common topology to kind of look at changes in resistance, and that's the Wheatstone bridge. Right, so this is the basic topology. Now I have 4 resistors instead of the 2 that I had earlier. In this case, I've labeled them R1, R2, R3, and R4. And these are basically just 2 voltage dividers in parallel. Right? I can compute the voltage here. Let's call this one the V minus node. Is just going to be a voltage divider with R2 and R1. So V minus is going to be R2 over R1 plus R2 times V in. And the same thing can be done for this V plus side with R3 and R4. In this case, I have R4 in the numerator, R3 plus R4 in the denominator, times V in. So if I'm interested in what V out is, right, I'm just going to subtract these two things. And V out is going to be equal to R4 over R3 plus R4 minus R2 over R1 plus R2, and that whole thing times V in. Right, so this is going to give me my V out when V out is defined this way, right? If I had the positive terminal on V out on the left side, I would just be flipping these two terms here. There are various ways to use that Wheatstone bridge topology. The first one we call the null measurement method. And in that method, we're trying to keep V out equal to 0, which implies that V minus is going to be equal to that V plus term, a condition in which we call the bridge balanced. And in this case, if I made my R1 resistor here a sensor, so say this was some nominal R1 resistance plus a change in resistance, then I would make my R2 component here to be a potentiometer. So this is now a potentiometer or a pot. And so as this resistance of the sensor changes, I can actually physically turn a potentiometer. The digital potentiometers also exist. If I physically turn that until V minus is equal to V plus, or that V out term is 0. And that balance condition is going to be true when R1 over R2 is equal to R3 over R4. Or if I'm interested in my sensor value here, when R1 is equal to R2 times R3 over R4. And this is the one that I would actually be adjusting physically or electronically in order to know what R1 is. So in that case, I would know R2, R3, and R4, and I would calculate then what R1 is. If I know the nominal value of that, then I can figure out what the delta R is. Ultimately, that's what I'm interested in figuring out, is what is the change in resistance based on some sensed value. Maybe it's a temperature, maybe it's a light, or something else. Another way to use a Wheatstone bridge is through the deflection method. And in this case, for simplicity, I've made R1, R2, R3, R4 all equal to R at their nominal resistance. I'm going to define this resistor up here. This one is going to be my sensor, so that's going to be the one that's changing. I'm going to measure my V out across these two terminals, as I mentioned already. And that R is going to be changing in the same way it did previously. So this will be an R plus a delta R, where the delta R is going to depend on that sensed value. And we already know from our basic bridge configuration, our basic bridge analysis, that my V out is equal to R4 over R3 plus R4 minus R2 over R1 plus R2 times V in. Now I can simplify this with the idea that everything is going to be equal to R. 2 1/2 minus R over 2R plus delta R, right? I've plugged in for this R1 resistor here, the R plus delta R term, and that whole thing times V in. And that ultimately simplifies down to a V out is equal to delta R over 4R plus 2 delta R times V in. So this is my final output voltage that's based on both my V in, the initial value of my resistances, and the change in resistance. And remember, this is ultimately, this delta R here, this is ultimately what I'm interested in. And in this case, it shows up in two places here. So this, similarly to our voltage divider, is also a nonlinear response to that change in resistance. It's also not very sensitive, and it's a little more complex. So the big question is why we use that. And you'll see why once we set this up in particular configurations beyond what we call here a quarter bridge circuit, where only one resistor in here is used as a sensor. Right? One thing I will point out though, before we take off here, is that I can, assuming that delta R over R in this case, or delta R is a lot smaller than R, then I can simplify this. So V out is approximately, in that case, delta R over 4R times V in. Right? So this is the kind of linear approximation of this equation, assuming that that change in resistance is very small in comparison to the initial resistances, the nominal resistances I have in the bridge circuit.